Assalamu alaikum students. I hope all of you are fine. Before starting today's lecture, let me revise one simple concept. All of you know this is D-type flip-flop, and its characteristic equation is Q next is equal to D. This is what you have already studied. Secondly, uh, in the previous lecture, I told you if you want to understand finite state machines, you need to know what are state transition graphs. Today we will see what are state transition graphs, but first we have to determine or we have to understand what is a graph. Here this G stands for graph. Now let us understand what is a graph. This is not a graph that you have studied in your earlier classes where you draw a plot in xy coordinates. Sometimes you call it a graph, but the graph I am talking about is totally different from this sketch. A graph is a set of nodes or points or vertices. These are nodes, points or vertices connected with edges. It can be any connection between all these nodes. This is node A, this is node B, this is node C, this is node D or vertex T. And these are edges. This is an example of a graph. This is a graph. These connections are known as edges, whereas these nodes, circles or points are known as vertices. These nodes are basically an abstraction. They represent something. For example, they can represent an LED or a state of a flip-flop or a register. These are abstractions, they can be anything. Whereas these are the connections. If these connections have arrows, you call it directed graph. If these arrows are not there, the graph is known as undirected graph. If you put arrows, the graph will become directed graph. Secondly, sometimes you put a weight here on edges. What does these weights represents? They represents, for example, if you are in state or node vertex A, if you want to change or transition from state A to B, you need a cost or weight A. You can say, for example, this is Lahore city and this is a Multan city. If you want to move from Lahore to Multan, you need C cost. Similarly, if you want to move from D to B, you need E cost. So these are the basic concepts that you need to know for the understanding of state transition graph that will be used in finite state machines. You will be in some state, you will transition from one state to another, and it will take some cost or change in input or output. Hopefully you have understood the definition of graphs. Now let us analyze our first sequential machine. In the next lecture, we will design a machine. But today, we are going to analyze our first finite state machine. Let's suppose we have two AND gates which are connected with an OR gate, and the output of this OR gate is going to a D type flip-flop, and its output is Q1. You know this is Q1 complement. This Q is going back to this AND gate. The second input of this AND gate is X. This X is also going to second AND gate. And let's suppose we have another flip-flop. This is Q2. So this will be Q2 bar. Here this Q2 is going to second AND gate. The input of second flip-flop is the output of an AND gate. The input of this AND gate is Q1 bar and X. These are the clocks. And we have another combinational logic, which is an OR gate, a NOT gate, and an AND gate. They are connected like this. The input of NOT gate is X. Whereas The input of OR gate is Q1 and Q2. This is your output. So if you compare this diagram from the diagram in previous lecture, you will see this portion is next state combinational logic. This portion is output combinational logic, and these two registers are state registers. Can any one of you guess, is it Mealy or Moore machine? Here you can see as I mentioned in previous lecture, these are present states, and these combinational logics are providing you next states. If your output combinational logic depends on previous state as well as the input, your sequential machine is of Mealy type. So this is a Mealy type finite state machine. Let's suppose this machine is given to you and you have to analyze it. For this purpose, the first thing is I am representing next states with Q1 plus, and here the next state is Q2 plus. The first step is you have to write Boolean equations for this next state combinational logic as well as for output combinational logic. So from this logic you can see Q1 plus is equal to Q dot X this is OR gate plus Q2 Q2 dot X. This is the Boolean equation of next state of first state register of flip-flop. Similarly, you can write an equation for this Q2. This Q2 plus is equal to Q1 complement dot input X. Here you can see this is input and this Q1 complement. Similarly, this Y is equal to Q1 plus Q2. You can see this is Q1. Here this Y is equal to Q2 plus Q1 with AND operation with x complement. This is NOT gate, so if you have x, you are getting x complement here. So these are three equations that are representing next state combinational logic as well as output combinational logic. So once you have written these equations, half of your job is done for the analysis of this sequential machine. So now let us start these Boolean equations to draw our or develop our state transition table. These are our equations. Let's suppose here this is Q1, this is Q2, and they are representing present states. Similarly, here you have Q1 plus Q2 plus Q1 plus Q2 plus for input is equal to 0, and these are next states for input is equal to 1, and all these states are your next states. And finally, you have your output y and y. This is your output y when x is equal to 0, and this is your output when x is equal to 1 or your input is equal to 1. This is your output. So now let us analyze our previous circuit. Let's suppose your present states are like this. Now, using these equations or the circuit diagram that is given here, you can fill these entries. So let's suppose first we calculate Q1 and Q2 next states for input is equal to 0. Here you can see when Q1 and X both are 0, you have 0 here, and when Q2 and these are also zeros, so 0 0 is 0. Similarly, Q2, which is basically the Q1 bar, because Q1 bar is 0, Q1 is 0, Q1 bar is 1, 1 dot 0 is again 0. And for output, when Q1 and Q2 both are zeros, this is 0, and 0 dot 1, because input is 0, you are getting 0. Now let me complete another row. I am now completing this row. where q1 is 1 and q2 is 0, and I am filling these values. For x is equal to 1. Here you can see when q1 and x1, sorry, q1 and x both are 1, this is 1 plus q2 is 0, but this is 0, it will be 1. So you will get 1 here. Similarly, for q2, your q1 is 1, this will be 0, 0 dot 1 is 0, you will get 0 here. And for this input is equal to 1, your output will be q1 is 1, q2 is 0, which is equal to 1, 1 dot 0 is 0. So your output will be 0 here. Using the same approach, your final table will look like this. You can confirm all the entries from this diagram also. So once you have achieved this state transition table, you can draw state transition graph from this table. It is also very simple. Now let us draw our state transition graph. This is your state transition table. Here you can see you have 2 bits in your state register. Possible number of states are 4, which are 0 0, 1 0, 0 1 and 1 1. These are your nodes or vertices of a state transition graph. So if you observe that if you apply an input x is equal to 0, your output is 0. So this is an edge that is pointing towards this 0 0. You are applying 0 and your output is 0. You are applying input x and your output is 0. And from this present state q1 q2 0 0, when you apply 0, you are moving to this next state which is also 0 0. That's why this edge is pointing towards itself, which is 0 0. Now let us apply x is equal to 1 when you are at state 0 0. In this case, when you apply an input x is equal to 1, this one, you are moving to state 0 1. It means you have to go there. When you apply an input 1, your output is 0 again. But this time you have moved from this state 0 0 to 0 1. Now let us start from this state 0 1. When you are at this state 0 1 and you apply an input x is equal to 0, you move to next state which is 0 0. So you are going here. When you apply 0 and when you apply 0 at this state, you are moving to 0 0 state and your output will be 1. Now let us check if we apply x is equal to 1 or input 1 from this state, you can see that if you apply x is equal to 1 at this state, you are moving to state 1 1. So from this state, you are moving here. What you have done is you have applied 1 and you are getting 0. Now you are at this state. At this state, if we apply input x is equal to 0, you are moving to state 0 0. It means you are going here. If you apply 0, and what the output you are getting is you are getting 1. So your output is 1 in this case. And if you are at state 1 1 and you apply input 1, you are moving to state 1 0. So in this case, you are moving here. When you apply 1 and the output you are getting is 0. Now you are at state 1 0. You are here. If you apply 0, you are moving to state 0 0 and the output you are getting is you are getting 1. Now as you are at state 1 0, if you apply input x is equal to 1, you are going to state 1 0. It means you are remaining in this state by applying 1, and the output you are getting is you are getting 0. Now the state transition graph is complete. It is representing or giving you all the information about your sequential machine. This is the analysis of this machine, in which you were given a sequential machine. The first step was you wrote next state combinational logic Boolean equations as well as output combinational logic Boolean equations. Using these equations, you developed state transition graph, or state transition table, and using this state transition table, you have constructed this state transition graph. This state transition graph is representing Mealy finite state machine that you have just analyzed. Hopefully you have understood the analysis of finite state machines. In the next lecture, we will design our first finite state machine. In the design of the finite state machine, we will use an opposite approach. You will be given a problem. From that problem, you will first develop a state transition graph. From that state transition graph, you will develop a state transition table. From that table, you will develop the circuitry of your sequential machine. So wait for next lecture and try to understand all the concepts that I have covered today and in my previous lecture, and try to read your textbook thoroughly so that you can easily understand the design of our first sequential machine. If you have any question, you are free to ask. My email address is given. You can contact me anytime. Thank you very much.